Hello children, welcome to my channel. This video is on the applications of Euclid's division lemma, which is a continuation of the chapter on real numbers. The previous video that I have already posted is on the division lemma itself. So as you can see, Euclid's division lemma says that given positive integers a and b, there exist integers q and r such that a is equal to bq plus r, where you can see this r is the remainder actually, q is the quotient, and a is the dividend, b is the divisor. This r remainder is such that it is going to be between 0 and b. 0 is less than or equal to r is less than b. Now let's go to a few applications of Euclid's division lemma. The first question that I've taken is show that any positive odd integer is of the form 4q plus 1 or 4q plus 3, where q is some integer. Now before I use the Euclid's division lemma in order to prove it mathematically, let me just take a few examples in order to explain to you what is the meaning of this particular question. Positive odd integer. Let me take an example of 13. As you can see, 13, when I write it as a multiple of 4, 4 into 3 is 12, and I am left with 1 as the remainder. If I take the number, suppose 39, then this is going to be 4 into 9, that is 36 plus 3. I am taking an odd integer. Let me take another odd integer, suppose that is 63. Then this is going to be 4 into 15 plus 3. As you can see, an odd integer is, if I want to write it as a multiple of 4, then my remainder is going to be either 1. My remainder is going to be either 1 or 3. So let's start with doing this mathematically with using Euclid's division lemma. So I am taking, let a be any positive integer, odd integer, because he's asking us about positive odd integer. Let a be any positive odd integer and b be equal to 4. Using Euclid's division lemma, I can write down a is equal to bq plus r, where 0 is less than or equal to r is less than b. Here my b is 4, and therefore I am writing down a is equal to 4q plus r, 0 is less than or equal to r is less than 4. Now when I am saying 0 is less than or equal to r is less than 4, it implies that r is either equal to 0 or 1 or 2 or 3. So when I take r is equal to 0, my a is going to be only 4q. If I take r is equal to 1, my a is equal to 4q plus 1. R is equal to 2 will give me a is equal to 4q plus 2, and r is equal to 3 is going to give me a is equal to 4q plus 3. But since I have assumed that a is any positive odd integer, it cannot be 4q, it cannot be 4q plus 2. So since a is any positive odd integer, a cannot be equal to 4q or 4q plus 2, which implies that a is of the form either 4q plus 1 or 4q plus 3. Let me take the next. So the second question is, show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5. Again, let me explain to you with the help of a few examples. The same example that we took earlier, if I take that, this is going to be 13 is equal to, if I want to write it as a multiple of 6, this is going to be 6 2s are 12 plus 1. In the same way, the next example, 39, is going to be 6 into 6, that is 6 6 are 36 plus 3. Let me take another example, that is 65. This is going to be 6 into 10, 60 plus 5. You see that every positive odd integer, these are the examples that I have taken, is giving me remainder of 1, 3 or 5 when I am writing it as a multiple of 6. So here, let a be any positive odd integer as in the question and b be equal to 6. Then using Euclid's division lemma, a is equal to bq plus r, where 0 is less than or equal to r is less than b. And here, because b is equal to 6, I am writing down b 0 is less than or equal to r is less than 6, implies r is equal to 0, 1, 2, 3, 4 or 5. So we get all these values up to r is equal to 5. You are saying a is equal to 6q plus 5. But again, like in the previous question, since my a over here is a positive odd integer, it cannot be equal to 6q. It cannot be equal to 6q plus 2. It cannot be equal to 6q plus 4. Implies my positive odd integer, that is a, is of the form either 6q plus 1 or 6q plus 3 or 6q plus 5. The third question, use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1. Now understand, the question is saying the square of any positive integer, square. Okay, so what I do over here is I am again starting in the same way. Let a be any positive odd integer and b be equal to 3. Then using Euclid's division lemma, I write down all this as we have done in the earlier questions, but now we have to square it. So here, first of all, r is going to be either equal to 0 or 1 or 2. So we have 3 possibilities for r, for the remainder. So when r is equal to 0, my a is going to be equal to 3q, and therefore the square of it, a square, is going to be 3q whole square, that is 9q square. Because I want to write it as 3 multiple of 3, I am splitting this 9 as 3 into 3q square, and therefore I get 3m, where m is equal to 3q square. If r is equal to 1, then from here r is equal to 1, my a is going to be equal to 3q plus 1. Now again I square it, so that is going to be a square. A square is going to become 3q plus 1 whole square. That is going to be a plus b whole square formula. So 9q square plus 2ab, 2 into 3q into 1 plus 1. This, from here I am writing it in such a way that it comes out with remainder 1. So 1 I leave it separately. From these first two terms, I take out 3 common, and therefore I get 3 into 3q square plus 2q, where my m is equal to 3q square plus 2q plus 1. For the last one, r is equal to 2. If r is equal to 2, I can write a is equal to 3q plus 2, and therefore squaring it, a square is equal to 3q plus 2 whole square. That is going to be 9q square plus 2ab, that is 2 into 3q into 2, that is 12q plus 4. Now I'm going to do a little bit of manipulation because I want remainder 1. So what I do is 4, I'm splitting it as 3 plus 1. And I keep this 1 separate, and I'm only looking at these 3 terms, first 3 terms. I'm taking out 3 common. I will get 3q square plus 4q plus 1 plus 1. That means I write this bracket as m. So I am again getting it in the form of 3m plus 1. And therefore I have proved that the square of any positive integer is of the form either 3m or 3m plus 1. So the fourth question is, show that n square minus 1 is divisible by 8 if n is a positive odd integer. Now let n be any positive odd integer. Now you have already done in the first question, I have already proved that if a number is a positive odd integer, it is of the form 4q plus 1 or 4q plus 3. So I'm going to use that I have already learned in my first question. So I'm going to say that since n is a positive odd integer, it is either of the form 4q plus 1 or it is of the form 4q plus 3. Then further, I'm going to look at what happens when you do n square minus 1. So if n is equal to 4q plus 1, n square minus 1 is going to be equal to 4q plus 1 whole square minus 1. I'm again using a plus b whole square formula, that is going to give me 16q square plus 2ab, that is 2 into 4q into 1, 8q plus 1 minus 1. When I open this bracket, plus 1 and minus 1 will go and I will get 16q square plus 8q. That will give me, I take out 8 common, 8 into 2q square plus q, which is divisible by 8, multiple of 8. Let's see for the next one, if n is equal to 4q plus 3. Then n square minus 1 will be this 4q plus 3 whole square minus 1. A plus b whole square, that is 4q whole square is 16q square plus 2 into 4q into 3, that is 24q plus 3 square 9 minus 1. This is going to be, when I open the bracket, 9 minus 1 is going to become 8, and therefore from all these three terms I take out 8 common, and that will give me in the bracket 2q square plus 3q plus 1, which is again divisible by 8 because it says 8 into something, meaning it is divisible by 8. Therefore, we have proved that n, if it's a positive odd integer, then n square minus 1 is divisible by 8. For any positive odd positive integer, here it's not an odd integer. The fifth question is, just show that for any positive integer n, prove that n cubed minus n is divisible by 6. Now this is a slightly different question. So what I've done is, first of all let n be any positive or positive integer. Now n cubed minus n can be written as n into n square minus 1, which when I further factorize, I will get n minus 1 into n plus 1. That is when I look at this, n into n square minus 1, which is going to be equal to n into n minus 1 into n plus 1. We want to show that this is divisible by 6. As you can see, n into n minus 1 into n plus 1 is actually, if you look at it, it is n minus 1 into n plus 1, meaning these three are consecutive integers. So if n is 8, 8 minus 1 is 7 and 8 plus 1 is 9. So 7 into 8 into 9. If n was say 13, then you would have said that would be equal to 12 into 13 into 14. So you are getting, because it is n minus 1 into n plus 1, you are getting 3 consecutive integers. Now let's start. Let n be any positive integer and b be equal to 6, because I want to show it is divisible by 6, which implies that n is equal to 6q or 6q plus 1 or 6q plus 2 or 3, 6q plus 3 or 6q plus 4 or 6q plus 5. Now over here, if we start with the first one, if n is equal to 6q, then n cube minus n is going to be, as we have written like this, this is going to be 6q minus 1 into 6q into 6q plus 1. If I take out 6 from all of them, if I take out 6 from 6q over here, I am going to get 6 into 6q minus 1 into q into 6q plus 1, which is divisible by 6. That is, this is divisible by 6 because it's a multiple of 6, meaning it is divisible by 6. In the same way, if I take n is equal to the next one, that is 6q plus 1, n cube minus n is going to be n minus 1 into n plus 1. So this is going to be 6q plus 1 minus 1 into 6q plus 1 into 6 cube plus 1 plus 1. So over here, plus 1 and minus 1 get cancelled. I will get only 6q. Here it is 6q plus 1, and here it becomes, this bracket will become 6q plus 2. Again, if I take out 6 common from here, the factor 6, inside the bracket I am left with q into 6q plus 1 into 6q plus 2, which is again divisible by 6. Similarly, I can prove for 6q plus 2 plus 3 plus 4 also. Let me show the last one, that is if n is equal to 6q plus 5. Then n cube minus n is equal to n minus 1 into n plus 1. So I will write down n minus 1 meaning 6q plus 5 minus 1 into n is 6q plus 5 into 6q plus 5 plus 1. When I further simplify, this is going to be 6q plus 4, 6q plus 5, 6q plus 6. From this factor, I take out 6 common, so I will get 6 into, in the bracket, 6q plus 4 into 6q plus 5 into q plus 1, because my 6 has gone out. So again, this is divisible by 6. Hence, we have proved that for any positive integer n cube minus n is divisible by 6. You can take any example and you can see that for any positive integer. So suppose I am taking n is equal to 3. Suppose n is equal to 3. Then my n cube minus n is going to be 3 cube, that is 27 minus 3. 27 minus 3 is equal to 24, and you can see this is a multiple, is divisible by 6. Is that clear to you?